Hydrogenase will give us a different way, although I think we've done it before, a different way of using our carbanion. Okay, so isocitrate dehydrogenase. So let's see, I get it behind the corner of the screen. So we've moved this. One consequence of citrate, right? We've got this hydroxyl group there. That's great. But we've got this hydroxyl group on a carbon with no hydrogens. So we can't oxidize that. And since the way we extract energy from these compounds is by oxidizing them, right? Removing the energy as high energy electrons in NAD or FAD. If we can't oxidize this, there's not much we can do with it. So one thing we get by moving the hydroxyl group here is we put the hydroxyl group on a carbon that has a hydrogen, which means that group becomes easier to oxidize. Right? That's one reason why we needed to move that. And so, right, here's our isocitrate, here's our hydroxyl group on a carbon with a hydrogen. We can oxidize that. That's the kind of chemical group that NAD can easily get involved in the oxidation. So we can directly transfer these two hydrogens as a hydride ion to NAD to make NADH. This hydrogen is removed as a hydrogen ion. And so we end up with this carbonyl oxalosuccinate. So we have an enzyme-bound intermediate of oxalosuccinate. Okay, now, we created a new carbonyl. So now this becomes a carbon alpha to that new carbonyl, which means this carbon can accept a negative charge. Well, it always could accept a negative charge stabilized by this carbonyl, but now it can accept a negative charge stabilized by this carbonyl. And that creates a situation on that carbon where we can easily decarboxylate. Right? So spontaneously, a pair of electrons from the oxygen can fall back. This whole carbon acts as leaving group. Right? Carbanion stabilized by this new carbonyl, carbon dioxide can leave. Actually, carbon dioxide, right? Since leaving has a specific connotation in organic chemistry, it's not the carbon dioxide that leaves, it's the rest of this molecule that takes the electrons and leaves. So in essence, by putting this carbonyl here, we make this carbon a good leaving group, so that we can create the carbon dioxide. Right? So they show the more stable form of the resonance stabilized anion, right? But at least a good chunk of the negative charge is going to be on that carbon, which we can then just protonate. And we are left with alpha ketoglutarate. So we took our 6 carbons in isocitrate, 1, 2, 3, 4, 5, 6, and now we are down to 5 carbons, alpha ketoglutarate. We've extracted some energy as NADH. We've created carbon dioxide. Okay? That make sense? Are we starting to see the patterns without me having to draw them every time? Right? How we're using carbanions, in this case, to break, we used a carbanion to make this bond when we made the citrate in the first place. And now we're using carbanions to our advantage to break this bond in our first decarboxylation. Question, Alan? Just not awake yet? Okay? Now, what makes this irreversible? The loss of carbon dioxide. Right? The loss of carbon dioxide makes this irreversible. What do we call that? What was our college word of the day? Metathetical. It makes it a metathetical reaction. Right? The equilibrium is disrupted because the carbon dioxide, as a gaseous product, eventually takes itself out of the equilibrium. Yes, sir?
So is it only reversible because it leaves the system? Like if you just had that floating around there, would you?
Would it reverse?
Take it back?
Huh, that's a good question. I don't know how high the concentration of carbon dioxide would have to get to make it reversible. That's a good question. Okay? Does that make sense? Kyle, we're happy to be part of this plan? Okay. Now, alpha-ketoglutarate. Now we're at alpha-ketoglutarate. Right? Alpha-ketoglutarate dehydrogenase. Has anybody read ahead? What's the problem if we just, from what we just talked about, if we look at alpha-ketoglutarate dehydrogenase, what looks funny about that? What do we say that NAD is good at oxidizing? Hydroxyl groups on carbons that have a hydrogen. Do we have a hydroxyl group that has carbon? No. So something funky is going on here. But we're getting an oxidation and a decarboxylation. We're going from a 5-carbon alpha-keto-carboxylic acid to a 4-carbon thioester. Right? So we're losing a carbon and creating a thioester. When have we done that before?
Did we switch?
Is that one?
What?
Pyruvate to acetyl-CoA.
Pyruvate to acetyl-CoA. Right? Pyruvate looks like this. Right? There's pyruvate. We're going to lose that and went to acetyl-CoA. Right? Isn't that essentially what we're doing here? Taking off a carboxyl group adjacent to a carbonyl and making it a CoA. What did it take to accomplish that with pyruvate?
An enzyme.
An enzyme. What was characteristic of that enzyme? What was characteristic of that enzyme?
Did it have an amine?
Yeah, well, I'm sure it did have an amine.
Different regions.
Not just different regions,
A lot of them.
big, right? Remember, it was big, it was complex. How many enzyme activities did it take? 3, right? It took 3 distinct enzyme activities. Actually, one of the enzymes actually did 2 things, right? Picked up the group over here, moved it over there, right? 3 distinct enzyme activities. Guess what? Same thing. This one is the same, right? Alpha-ketoglutarate dehydrogenase structurally is very similar to pyruvate dehydrogenase. Right? As a matter of fact, it shares E2 and E3 subunits with pyruvate dehydrogenase. E1 is distinct, actually let's say it's unique to alpha-ketoglutarate dehydrogenase. Why does alpha-ketoglutarate dehydrogenase need its own E1? Ellen? To recognize that it's alpha-ketoglutarate, yeah. Right? Remember, it's E1 that actually interacts with this initial substrate. And so the pyruvate dehydrogenase E1 recognizes pyruvate. The alpha-ketoglutarate dehydrogenase E1 recognizes alpha-ketoglutarate. It's no more complex than that. Yeah?
So you're just saying that structurally E2 and E3 are exactly the same, or that literally the protein complex, like they share the same E2 and E3, like alpha-ketoglutarate goes through there and pyruvate goes through there?
Structurally they share, they're the same. The same gene is used to make the E2 that is used in pyruvate dehydrogenase and alpha-ketoglutarate dehydrogenase. The same gene is used to make the E3 that's used in alpha-ketoglutarate dehydrogenase and pyruvate dehydrogenase. But different genes are used to make the E1 that's used for alpha-ketoglutarate dehydrogenase and pyruvate dehydrogenase. Does that make it clearer, saying it that way? The other big difference here, and the other thing that makes E1 different, there's no kinase, phosphatase, control system in alpha-ketoglutarate dehydrogenase like we had with pyruvate dehydrogenase. So the big difference in the alpha-ketoglutarate dehydrogenase complex, it has its own unique E1, and it doesn't have the associated kinase and phosphatase that we see with pyruvate dehydrogenase. Does that make sense? So it's controlled only by availability of free coenzyme A, availability of free NAD and NADH. That's what controls the flow through alpha-ketoglutarate dehydrogenase. Is NAD available? Is coenzyme A available? Okay? So otherwise, everything we said about the pyruvate dehydrogenase complex applies to the alpha-ketoglutarate dehydrogenase complex. Okay? All the chemistry we talked about, all the mechanisms we talked about, all the same. All the other coenzymes, thiamine pyrophosphate,